Hello, everyone. Welcome to pre-lecture number 13. Today, we're going to be talking about solving some more complex equilibrium problems, and this is mainly going to consist of an example. Okay, so thus far, when we've been computing answers to our equilibrium problems, we have solved for basically an unknown given the concentration of either all of our reactants or some of our reactants of products. And solving for K has been one question we've done. Alternatively, like last class, we've been given the concentration of one of our reactants and one of the products, and we've been able to figure out all of our other species from K or Q through the use of an ice chart. And so this was just an example that we did from in class last time where we had this HNO2. We were given an initial amount. We were told the concentration of one of our reactants at equilibrium and asked to calculate Kc. And so these have been good starter problems, but we're actually going to level it up one more time here, where what happens or how do we solve problems when we are only given starting concentrations or final concentrations and the K value of a reaction. So in order to do this, we need to use a more complex strategy. And this is something that we're going to be using, obviously, this unit and pretty much all of next unit. So would recommend learning this strategy well. And obviously, if you have any questions, please let me know via email or during class. And so this is the example problem we're going to be doing in the video for today. And so pull up my drawing tool here, and then we can get going. So in this example problem, we have this reaction, SO2Cl2, dissociating into SO2 and Cl2, and it has a given K value there of 2.99 times 10 to the negative 7. If a reaction mixture initially contains this 0.175 molar of our reactant, what is our equilibrium concentration of Cl2? I will also point out this is problem number 13 on our chapter 13 in-class worksheet. And so if you would like to solve along in that spot, you of course could. Okay, so the first step for solving a problem like this is going to be similar to basically all of our equilibrium problems, where I would recommend rewriting your chemical equation and then also writing any sort of equilibrium expression. Okay. So if I do that, we have SO2Cl2 gas plus, or rather dissociating into SO2 gas and Cl2, which is also a gas. And so because all of our species are gases, that means, of course, that we will consider all of them in our equilibrium calculations. We can also write out an equilibrium expression, which, remember our mantra, products over reactants. And so because our stoichiometry is 1 for all of these species, it will just be our concentration of SO2 times our concentration of Cl2 over our concentration of SO2Cl2. Right? So just our products over our reactants there. And then our next step is going to be the same that we did last class. So we're going to make an ice chart. So ICE, which again stands for our initial concentrations, our changing concentrations, and then our equilibrium concentrations. Okay. This time we're only given our initial concentration of our reactant. And so we can, of course, go ahead and write that in. That's 0.0175 molar. And because we're not told any information about our products, we can assume that they have a concentration of 0 at the start. So if we want to get those units, we can label them 0 molar. Since we don't know anything about our concentrations at equilibrium, the next thing I'm going to fill out is actually our change. And so we know that since we're starting with just reactants, we're going to lose reactant. And so that's going to be minus x. And because we have a 1-to-1-to-1 stoichiometry, we know that for every mole of our reactant we dissociate, we're going to get 1 mole of each of our products. This is just a dissociation reaction, right? And so we don't know what x is at the moment. That's really what we're solving for here. But essentially, we can just say our change is going to be minus x for our reactants plus x for our products. And then at equilibrium, we essentially just combine these two. And so we know at equilibrium, our concentration of SO2Cl2 is just going to be 0.175 minus x. And we know that our concentration of both SO2 and Cl2 at equilibrium is going to be equal to our value of x. Okay. And so if we were to plug all this into our equilibrium expression, we are given the value for Kc. And so we could say that 2.99 times 10 to the minus 7 is equal to our, instead of putting our concentrations here, just since we don't know them, we're still with variables. And so I'll just put x multiplied by x, which is what we know our concentration of SO2 and Cl2 will be, and then divided by this 0.175 molar minus x. Okay. So all I did in this expression is just plug in the line values for all of our equilibrium expressions here. So I plugged in x's and then 0.175 molar minus x. Okay. So if we were to essentially combine some terms and rearrange this equation, what would happen is we could combine our x terms and try and get everything on all of our variables onto the same side of an equation. And so what that's going to look like, what I'm going to essentially do here is multiply this term up. So just using algebraic manipulation, multiply that up, and then I'm going to combine these two x's into just x squared. And then I'm going to subtract that from our other side to set this equation equal to 0. And so when I do that, I should get a value of 5.233, which is just our 0.175 molar term multiplied by this. I'm going to subtract because we have minus x there. This will then, if we distribute this term through, our term in parentheses here through our Kc value, then we would have minus 2.99 times 10 to the minus 7x. And then if we also subtracted over our x squared value, we would subtract x squared, and ultimately this would be equal to 0. Okay. And so what we've ultimately done here is we've created an equation that can be solved using the quadratic equation, right? Because we have an a term, a b term, and a c term, where our a term has a quadratic function, so squared. Our b term has just one x variable, and then our c term has no x's in it. And so for those of you that don't remember the quadratic equation, it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times c as well, or 2 times a as well, sorry. And so if we were to write that out to solve for x, we could say, again, with these different terms being our a, our b, and our c, the a term in particular is going to be 1 because we look for the coefficient in front of that. So plugging this all in, x equals negative b, so b is our 2.99 times 10, or our minus 2.99 times 10 to the negative 7th, so minus times minus 2.99 times 10 to the minus 7th, and then that will be plus or minus, so we're going to get 2 solutions to our quadratic equation. And so this is then the square root of b squared, so b again, 2.99 times 10 to the minus 7th squared minus 4a. So a is just 1, and then c is 5.233 times 10 to the minus 8. I apparently forgot that here, so when we multiply 2.99 times 10 to the minus 7th times 1.175, this should be 5.233 times 10 to the minus 8th. Sorry about that. And so we take the square root of all that term, and then we divide all of this by 2a, and so a again is just 1. Okay. And so if you plug all this into your calculator, you should be able to solve for x. And so x will have two answers because we have a plus and a minus for the quadratic equation. And so the two answers are either negative 2.29 times 10 to the minus 4, or 2.29 times 10 to the fourth. Negative fourth still, sorry. So we essentially have a positive and a negative value. And because x represents a real thing, x represents our concentration, right? We know that we can't have a negative concentration. And so this first answer, this negative value, is going to be essentially just non-logical. And so we know that our answer for x is going to be this 2.29 times 10 to the minus 4. Okay? That is what x is equal to. And so ultimately, because this question asks what's our equilibrium concentration of chloride, or chlorine rather, Cl2, we know that because x is equal to the value of Cl2, according to our ice chart, the concentration of our chlorine at equilibrium is going to be equal to this 2.29 times 10 to the minus 4th, and then we would add in molarity there, because that is, of course, the units that we solved in. Okay? Right, so that is how you would solve that equation using the quadratic formula. And so if you'd like to pause your video, take any notes, write down any questions, you could right now. I'm going to show you a slightly different way. So using a very similar method, but we can actually take a shortcut that saves us some time here. And so I'm going to erase some of this work. And so give me one moment to do that, and then we will go through a potential shortcut here. All right, so if we still do the same thing, start with our ice table, and then write out our equilibrium expression. We can basically, once we get to this point where we have our equilibrium expression being equal to our values here, and I'm going to change colors so that we can see the shortcut method here, or where it starts off. So we can make an assumption here that x is going to be a small value. And so this is called the x is small approximation or shortcut. And so if we assume x is going to be some small value, in particular, if it's going to be much smaller than our starting concentration here, then what we can do is just ignore this x term in our denominator. And so when we do that, our expression turns into 2.99 times 10 to the minus 7th is equal to x squared over 0.175. Okay, and when we do that, we no longer have to solve a quadratic equation. And so if we just solve this algebraically now, We multiply this 0.175 up, multiplied by our equilibrium constant, and we should get a value of 5.2325. This is, of course, not with significant digits, but I'm just carrying a few extras through for rounding purposes. That will be equal to x squared. We then take the square root of each side. Then we should get that x is equal to 2.29 times 10 to the minus fourth molar. And so you might notice this is the same exact value that we got using the quadratic equation. And so that is generally a good indication that x can be considered small. Essentially, we can take this shortcut and not use the full quadratic equation. But let me show you real quick how to check to make sure that this assumption is valid. And so once you determine a value for x here, what you'll want to do is check it against your initial concentration to make sure that it is less than 5% different. So let me write that down. So 5% difference is our cutoff. And so how we check that is we would take this 2.29 times 10 to the minus fourth, divide it by our initial concentration, which is, of course, the 1.75 molar. We should add molar for each of these. Multiply it by 100 in order to get a percentage. And so when we do that for this equation, I got a value of 0.13%, which is, of course, less than 5%. And so as long as this value that you calculate is less than 5%, that means that this is a valid assumption. Okay, so you might get a slightly different answer, but it shouldn't be significantly different if we consider our significant digits. Okay. All right, so that is how we solve for an unknown concentration at equilibrium if we're only given reactants. We will do a bit more of practice in class with this, and so I hope that was helpful. Obviously, with this video, feel free to rewind, watch it multiple times, and hopefully it will help you understand how to do this better. But if you have questions, please feel free to email or let me know in class. Okay, going to clear those drawings. And let's see, Avogadro says, have a good day, which I hope you do. And I will see you in class.